Water is an important and limited resource in the American Southwest. Temporary storage of this precious water may occur in groundwater, lakes, streams, and wetlands. Wetlands are particularly rare ecosystems, comprising only a small percent of the land area. These meadows are beautiful features in our western forests, but in addition to their beauty, wetland meadows provide many essential ecosystem services, such as nutrient storage, flood and erosion prevention, and vital habitat for plants and animals. Unfortunately, many of these meadows are severely eroded, which alters the riparian habitat and reduces water storage capacity. Until the 1880s, most wetland meadows in the Southwest were relatively broad and flat, with a gracefully meandering stream slowly winding back and forth across their floodplains. Sometime around 1880, the so-called arroyo cutting event took place. Possibly triggered by a combination of climate change and land use, this event has cut a deep swath through the meadows. In many cases, the rich soil has been incised all the way to bedrock. This robs the meadow of its ability to store and filter water in this otherwise deep layer of alluvium or deposited sediment. Researchers and forest managers are working to stabilize these wet meadows. The first step is to understand as much as possible about how each channel was formed. Geologists, geomorphologists, and hydrologists study the channel and surrounding watershed in great detail. They are, in effect, charting the history and evolution of the stream. After the stream's evolution is understood, engineers use computer models to discover the best way of realigning the channel to reduce erosion and restore it to its natural, unincised condition. Finally, botanists and foresters revegetate the affected areas. All natural systems are complex, and understanding them requires an interdisciplinary research approach. Success depends on combining the varied expertise of geologists, geomorphologists, hydrologists, engineers, botanists, and foresters toward a common goal of improving ecosystem form and function. On a smaller scale, these types of projects have been underway for several years. One such site is Clover Springs, where the channel has been successfully stabilized and revegetation is well underway.
So this is where the old channel used to connect up to our restored channel, and we actually took the old Lowhead Dam that used to be here and filled in. This used to be channel right here, downcut channel, and we relocated the channel through this meander, and the channel here you can see is already starting to evolve to what we'd like. Slightly downcut, overhanging with sedge, armored with boulders. Again, the reach of the channel in the elk exclosure is what we think is a more stable type of configuration, where we have native vegetation that comes down to the sides of the channel and overhangs, a slightly downcut portion of channel that's armored with local rock in the bottom. Under most spring flows, which are usually pretty low, the channel only stays down in this slightly downcut part. But when there's snow melt in really high amounts, that flow exceeds this smaller channel and goes up onto this upper channel, which is stabilized by the dense mat of vegetation. So we anticipate on the reaches we're restoring here that we're going to nudge the natural system to coming back to this state of equilibrium sooner. Left on its own devices, the streams have a way of coming back to a state of equilibrium, and vegetation would come in on its own. That might take, though, tens to hundreds of years. So we hope by our earth moving and our revegetation that we can return it to that more stable natural configuration sooner than it would on its own. Other things we had to do at Hawksworth, we did involve other people at various stages of the process. We had to survey for threatened and endangered species. We had to do archaeological surveys and look for historic preservation features. We had to get clearance from the Army Corps of Engineers under guidelines of the Clean Water Act. So we did get input from a lot of other people.
Meadow systems are very vibrant ecosystems when they're functioning properly because they have a lot of biodiversity, plant biodiversity as well as fauna biodiversity. And when you have a lot of plant biodiversity, you get a lot of insects. Low portion of the totem pole as far as the food chain is concerned, but it provides a lot of food for small birds, and the small birds provide food for raptors and so forth, so on you move up the food chain. They're also very key for water storage, and also as large sieves, they provide clean water coming out of the system when they're functioning properly. And Clover Springs before was not functioning properly. It was downcut fairly severely, starting to widen out a bit, but it was still providing quite a bit of sediment to the system. Water flows through it were a lot flashier. That means they were a lot more efficient. When we'd get a storm system, that channel would really move water through the system quickly, so our peak flows were higher. That made more potential flooding impacts downstream, as well as not leaving water on the mountain as long to provide for habitat and also water for riparian-dependent species.
The current study area is centered on Clover Springs in the Mogollon Rim country of Arizona. The project is a cooperative venture between the Coconino National Forest, the Arizona Water Protection Fund Commission, Northern Arizona University, and the Arizona Department of Environmental Quality. Clover Springs is located along a half-mile reach of 44 Canyon. As part of the Coconino National Forest, the Mogollon Rim rises abruptly 2,000 feet above the Verde Valley to an average elevation of 7,000 feet. As humid air is forced to rise up this escarpment, it cools and condenses, giving this area over 36 inches of rainfall per year, the highest amount of rainfall in the state. The Clover Springs Interdisciplinary Research Team was charged with developing a restoration and stabilization plan that would improve the wetland meadow and restore its ecosystem functions. Geomorphic analyses indicated that the soil depth in this valley floor had been slowly and steadily increasing for the past 7,000 years. This was discovered through radiocarbon dating of the deposits, sediment and soils analyses, tree ring dating, and mapping. 7,000 years of soil buildup was abruptly halted at the turn of the century when the channel incised to bedrock.
The entrenchment episode is found throughout the Southwest, and there's hardly any valley floor that you can go to in the Southwest and not see these deep arroyos. And they've really changed the ecosystem in the valley floors quite a bit. And part of our goal is to reestablish that wetland meadow that used to exist in that area. For the Clover Springs Reach, what we found is that the channel entrenched after some road building in the area. And what we think happened is that the channel, which normally meanders all over the valley floor, is actually constrained to a narrow reach. And when you constrain the stream and you straighten it, which is what was done to try and keep it away from the road, we think, you increase its gradient. And when the gradient is increased, it's steepened, it tends to initiate head cuts. And what a head cut is actually kind of a little waterfall in the alluvium, which is a little area where we go from one elevation of stream to another. And that thing migrates upstream. If you can visualize a flood event flowing over the lip of that little waterfall or that head cut, it will start to erode at the edge of the head cut, and so that head cut moves upstream, and that's what happened in Clover. The head cut in Clover has actually moved through Clover and out of Clover Springs area, and it's migrating upstream beyond our field area. Our project area is constrained by a couple of factors. There's a culvert that goes under Highway 87 that provides kind of a tie-down point for the stream level on the upper end of the valley. And then there's bedrock at the lower end of the valley. So the highest elevation, the lowest elevation that the stream has to work with, that we have to work with, is tied down. within those 2 points, what we're trying to do is reduce the gradient of the stream. And so to do that between 2 points, one of the ways to do that is to actually allow it to meander back just like it used to, which will take up some of the gradient and allow the channel to be, the channel floor to actually be of a lower slope than if it was just straight. So we've actually in a way, extended the length of the stream by causing it to meander, which is what it used to do. The purpose is to reestablish the wetland meadow. And so in order to do that, we need to bring the channel back up onto the floodplain and get it out of the hole that it's kind of stuck in, the entrenched arroyo that it's stuck in.
Before breaking ground on any stabilization project, the scientific team must complete years of sampling, monitoring, and hydrologic modeling of the watershed. This allows engineers, using a wide variety of specialized computer software, to design a channel shape and pattern that is stable under natural conditions.
Essentially, your watershed's thirsty, it rains, water percolates into the ground. At a certain point, the interstitial matrices of the soil reach their threshold capacity and water starts to run. And we were able to calibrate to that watershed loss function using the SCS curve number method with the given measurements of precipitation and runoff, which helped us build confidence in our ultimate model that we used to develop bankful discharge, because we had a good idea as far as calibration on that watershed loss function.
The engineering plan had 3 goals: to reconfigure the channel, to lessen its gradient, and to redirect the stream back onto the now abandoned floodplain. The channel design was based on computer modeling and studies of similar unentrenched systems. After 2 years of very careful study and planning, the construction phase finally began. It required moving 15,000 cubic yards of earth, 19 days, and lots of heavy equipment.
The construction is quite an interesting thing. You know, if I think back to when we first started, there were a number of earth movers, bulldozers, if you will. I think they were D5s, a couple of those. One front end loader, a couple of haul trucks. And so it was interesting to see all that stuff out there, and probably caused some people some concern, you know, as far as those who were unfamiliar with channel restoration. You know, it's a bit of a daunting process. Lots of dirt. I think it ended up being 12 to 15,000 cubic yards or something like that, plus or minus 1,000 or 2. But it was a lot. And so we progressed from the upstream end as long as we had stuff to dig and as long as we had stuff to fill, like basically moving dirt from here to over there and filling holes along the way. The reason that you have a meander in here is that will minimize or keep your gradient, again, your drop in elevation over stream length, will keep your gradient low. So what happens when you straighten it out is that it increases the gradient, makes it steeper, and then will therefore increase the velocity of the water moving through that channel. The increased velocity you can think of as increased energy, and that energy is pounding against your banks and pounding into your bed, causing down cutting and bank erosion. Hopefully in years to come, people will go out there and not recognize that we've been there, and which is kind of interesting from an engineering point of view. One might often want to have testaments to one's presence and effectiveness. And the testament here would be that they don't know we were there. We had very, very good equipment operators, and these guys, you know, with these big old pieces of equipment, were able to get within less than 1/10 of a foot accuracy from the design specifications. Just some really good operators. These were Forest Service operators too, I might add.
A very talented bunch of individuals there. All work locally on the forest. They could do anything, and that's what you need when you have a project like this. You have to have a jack of all trades, and we happen to have about a half dozen jack of all trades on this. That they could jump from one piece of equipment to the next. They could put fence up. They could help plant grass. They could hydromulch. They could do anything, and they're also fun to work with too. That makes a big difference. You know, they have a real good attitude, and plus they really enjoyed the project because it was challenging, and they enjoy a challenge.
It's a rough business, you know. You bang around on the Coconino Plateau. Being in this potato dirt is a real rarity. It's usually on solid rock, and electronic connections just end up getting beat up pretty bad. And then it's a filthy environment, you know. There's a lot of dirt, and then the moisture gets the dirt kind of muddy, and things short out. But it won't be too long, and we'll be right back up and running.
Because it was constrained by the roadbed of the nearby highway, the upper part of the reach was simply widened to form gently sloping banks. In the lower part of the Clover Springs reach, the old arroyo was filled in and a new stream channel was established. The new channel has a very different look and shape. It is more sinuous, winding back and forth across the entire floodplain. It is also much longer and shallower. Revegetation took place immediately following the construction activities. It consisted of hydro-mulching, hand-transplanting sedges and rushes, and securing erosion mats. An 8-foot-high fence was constructed around the lower portion of the field area to protect it from elk grazing while the vegetation became established.
By putting up some temporary exclosures, basically a very tall fence that the elk can't jump, it gives the vegetation a chance to get their roots established. Then the vegetation should be able to handle the numbers of animals that would come in once we take the fence away. When you restore areas, you do a lot of disturbance, and many invasive exotics are better competitors than our native plants. If we just leave it to seed, a lot of times the native vegetation has been lost. In the case of Clover Springs, there should be a lot of sedges and rushes all up and down the channel, and most of those have been lost because when the system dried out, the sedges and rushes tend to be more wetland-oriented type plants, and they were essentially lost from the system. So there's no seed source for those to come in, which is why a lot of the less desirable exotic plants would move in. So it's important to go in and try to get the native vegetation to have more of a head start, essentially.
The research team is pleased by the results to date. The channel has proven capable of handling high peak discharges, and the revegetation efforts have resulted in a great diversity of species.
These sedges are unbelievable, and we're starting to get natural regeneration from them through seed, and also these have just expanded. That was a plug that was that big around. It's expanded into 2 separate plants. These things are really starting to come on here. The idea behind these, they have very fibrous root systems that will hold this system together, or actually, because most of this is pretty fine material and it's very susceptible to washing. These root systems, you know, primarily have 40 to 50 times more root mass per unit area than Kentucky bluegrass, which is what was in here before. Kentucky bluegrass would roll up and just roll away. This is what's going to hold it, are these native riparian dependent grasses in here. Some very productive soil down here. So he's got, what, 4 or 5 feet of growth on him this year. We expect to see more of them. More aspen coming down the hill from that clone there. Here's one we want to get rid of. That is a bull thistle. That's a noxious weed. Here's our native thistle. And what you can see crawling on my hand are ants, and that's one of what we get with all these different plant species are a lot of different insects in here that provide prey base for smaller animals. Obviously got bees working in here, so starting to get some
some natural function in here. And that's what we want to get into the meadow is natural function, where this meadow can handle stream flows because of the dimension pattern profile and because of the vegetation in here. When I say dimension, pattern, and profile, the pattern of the stream dissipates stream energy by adding increased length through here. This thing was down cut, straight shot through here. We've added an additional 300 to 400 feet of stream length in here, which what that does, it decreases slope length, which decreases stream energy, so the water can stay more on site. A lot of bees in here. Pretty busy. Starting to get some voles. We had voles in here before, but voles are, we have research on the Mogollon Rim here. In properly functioning ecosystems, our vole populations are 20 to 30 times more what we do in ones that are not properly functioning. And what that does, it provides prey base for raptors, and specifically provides prey base for Mexican spotted owl, which is a threatened species. So there's a lot of stuff going on. So this is not a simple system. No systems are simple. I'm basically standing within the old channel. I would have been channel would have been 3 to 4 feet above my head. Deeply incised channel, very efficient channel for moving water, very efficient for moving water. This thing, what we believe happened, but we don't have confirmation of it. First of all, it got grazed very heavily at the turn of the century, which had some effects. But the main effects was when we constructed State Highway 87. We think they straightened this channel out because the 1948 aerial photos show a almost tortuously meandering stream across this. That's how it helped dissipate energy. But once we had a straightened channel, it really downcut and became very efficient at moving water off the system, which increased peak flows, which affects downstream resources, affects water quality. And we've actually connected to the old floodplain in here. Once we hit a bank full discharge stage, it will actually be reconnected to the old floodplain. So it'll fill that channel, dissipate across here, and that will really slow water movement down across through here. But this is what we want to try to achieve, and so far so good. Still want to get more vegetation reestablished. We picked the driest year in the world to get our revegetation started, but it's coming along quite well, and we expect it to improve over the years.
The techniques developed from this interdisciplinary project may be used to stabilize other degraded wetland meadows. This project was funded by the Arizona Water Protection Fund. One of the goals of the AWPF is to develop and implement measures to enhance and restore streams and their associated riparian habitat. The Clover Springs project will restore form and function to the wetland meadow and is an excellent opportunity to provide information about ongoing research to the public.